Greetings, Panthers. Dr. Augustine again. Today we're going to talk about finding empirical and molecular formulas from experimental data. So this would be if you did a certain experiment, you got some information from that experiment, and you needed to find the empirical formula and the molecular formula. You'd have different pieces of information in order to do that. We'll talk about how that works in a few minutes. So this video also covers Chapter 3.9, Intro. This is the second part of Chapter 3.9. And the topics we're going to cover is how do you determine the empirical formula for a compound given its mass percent composition. If you don't know what that is, go take a look at the prior video which talked about what mass percent composition is. So if we're given that information, the mass percent composition, or we found it somehow, this would tell us how to find the empirical formula. And the second part of this video, the second half of this video, will be determine how you can determine the molecular formula if you, one, know the empirical formula, in other words, you just did the prior step, and two, the molecular mass of the compound is given to you. So before we do this, before we dive into this, I want to make sure that we know what these words mean, empirical formula and molecular formula. So an example of this would be something like benzene. This is a typical organic compound, and the molecular formula for this is C6H6. Okay, if you found this thing out in nature, it would have 6 carbons and 6 hydrogens. They happen to be arranged in the structural formula that looks sort of like this. It's a famous ring with alternating double bonds. The ball and stick model looks like this, and the space filling model looks basically like this. A flat molecule with 1 hydrogen attached to every carbon. Every carbon is attached to 2 other carbons and 1 hydrogen, okay, to form this ring structure. That's the molecular formula. The empirical formula is when you divide through by a common factor. So if we were to divide through by 6, we'd end up with a formula of CH. That's the empirical formula. Now you might ask, why would you use the empirical formula, or why is that necessary? Isn't this a more useful way to describe it? Well, the answer is yes, that is a more useful way to describe it. However, sometimes experimentally, when certain experiments are done, you can only find the empirical formula. You would need to have other information in order to figure out the molecular formula. So let's take a look at the empirical formula first, and then we're going to take the same compound and figure out what the molecular formula is, given a little more information. All right, so the question is, determine the empirical formula of a compound that only contains carbon, hydrogen, and oxygen. This would be a typical hydrocarbon. Many different compounds contain just carbon, hydrogen, and oxygen. It contains the following mass percent composition as experimentally determined. Remember in the last video, if you watched it, mass percent composition was the percentage of each element in the compound as determined by different experimental techniques. One would be something like a mass analysis. So we're given in this problem 52.14% carbon, 34.73% oxygen. So maybe experimentally we did this and we determined that there were actually 2 different elements in it, and they had the following percent compositions by mass. And we want to find out what the empirical formula is of carbon, hydrogen, and oxygen. We know there's hydrogen in there also. So the first thing we should note is, well, we're not given the information about hydrogen. So a good question you can ask is, what is the mass percent of hydrogen? So that's actually pretty easy to determine. We know that this compound is made up of 3 different things. We also know that we're given the percentages of carbon and oxygen, so hydrogen must be whatever the difference is from 100%. So we have something like this, 100 minus 52.14 plus 34.73. And that quantity is going to be equal to 13.13% hydrogen. Okay, so those are our 3 mass percentages that we have in this compound. Those should, of course, add up to 100 since we just subtracted it. All right, now this is asking for the empirical formula. So we're going to have some structure that looks like C something, H something, O something. And we're trying to figure out what this X, Y, and Z is from this compound. So here's the easiest way to do this, or here's a consistent way to do this. Let's pretend that we have 100 grams of this compound. All right, so we're going to make an assumption. We're going to assume assume that we're starting with 100 grams of this compound. Why are we assuming that we have 100 grams? Well, that makes a pretty convenient number because then I can convert these percentages into grams, because if I know it's 52.14% carbon, if I had 100 grams, it would also be 52.14 grams of carbon and 34.73 grams of oxygen and 13.13 grams of hydrogen. Okay, so that's a convenient little trick you can do. If you assume you have 100 grams, then you can immediately turn those percentages into masses. Okay, so I want to show you something that's incorrect, and I want to show you why. So we're going to start with getting an understanding of what this formula really has to do with. 52.14 hydrogen, 13.13, oxygen 34.73. And I want to tell you that this is incorrect, okay? And here's the logic behind this. When I have a chemical formula, let's take something like water, take a nice easy one. So I have H2O. H2O consists of 2 hydrogen atoms and 1 oxygen atom. It also means 2 moles of hydrogen for every 1 mole of oxygen. But it is not telling me about the mass ratio. It's telling me about the atom ratio, and it's telling me about the mole ratio, but it's not telling me about the mass ratio. So I'm just going to write this down as a reminder to you. So when I have a correct formula, we'll take C6H6 as my formula. It's giving me the atom ratio, that there's 6 carbons for every 6 hydrogens. It's giving me the mole ratio, but does not give me the mass ratio. C6H6 is more obvious. Carbon is 12 times heavier than hydrogen. So even though there's the same number of carbons and hydrogens, the mass of carbon is way more than the mass of hydrogen. In fact, carbon weighs 12 times more than the hydrogen that's in that molecule. So we cannot look at the masses, or these mass percentages cannot be plugged directly into an equation because the formula does not tell us anything about the masses. It tells us about atoms and it tells us about moles, and they're the same. The atom ratio and the mole ratio are the same, but it does not tell the mass ratio. Okay, that's a key concept that you might want to sort of make a note to yourself or star or make something to sort of indicate that this is a key conceptual idea. Okay, but if we do have the masses of each of these, then I can find the number of moles of each of these. And if I can find the number of moles, then those become mole ratios. So let's take a look at that. This might be a good place to stop the video if you want. Let's find the number of moles of each of these atoms, carbon, hydrogen, and oxygen, and then put them into a mole ratio. Okay, so you should have had 3 calculations for moles carbon, moles hydrogen, and moles oxygen. Start with the mass, 52.14 grams of carbon times 1 mole of carbon for every 12.01 grams of carbon. That gives us 4.34 moles of carbon. Just to see, make sure the units are canceling. Grams carbon should cancel grams carbon, grams oxygen, grams oxygen, grams hydrogen, leaving us moles. And one more thing you should know, this is a common mistake that students make. This is grams of oxygen, atomic oxygen. It's not O2. Okay, it's atomic oxygen. So 1 mole of atomic oxygen is 16 grams of atomic oxygen. Students will often put 32 grams in here because they're used to oxygen being in the form of O2. But for this type of calculation, it's not O2, it's not the molecular oxygen, it's atomic oxygen. So 1 mole oxygen for every 16 grams. That gives me moles of carbon, hydrogen, and oxygen. Okay, so we can take our CXHYOZ and we can now put in the number of moles that we just found. C 4.34, H 13.03, and O 2.17. Now at this point, I'm going to ask the question, which I always ask my class, is this the correct formula? Is this the correct empirical formula for this compound? And I usually get some scrunched up faces saying, oh no, that's terrible, that's not right. And the reason is we're used to formulas having the correct whole numbers. Technically, this is in the right mole ratio. It's just we don't like these decimals. Okay, so we're not going to leave it here, but at this point, this is in the correct mole ratio. So how can we get rid of these? How can we get rid of these decimals? The way to do that is to divide by the smallest factor. In this case, 2.17 is the smallest factor. So I'm going to divide each of these numbers by 2.17. And when we do that, we get something like this, C2H6O. That becomes my empirical formula. That's the simplest formula that we can have. We can't divide by a common factor. And we've determined this, just to review how we got here. We determined this by starting with percentages, assuming we had 100 grams of this stuff, which means those percentages turn into masses. We need to then turn those masses into moles, put that into a mole ratio, divide through by a common factor, and you end up with the empirical formula. Now, you could have a case where they're not going to work out exactly right. Let's say we have something like, I'm just going to make this up, KCRO 3.5, let's say. That's possible. You could end up with something with a decimal. So the way we're going to do that is we need to clear that decimal out. And if we have a thing that ends with a 0.5, if we multiply everything through by 2, that'll make it a whole number. If we have 0.33, we can multiply through by 3. If we have 0.24 or 0.25, we can multiply through by 4. If we have 0.20, we can multiply through by 5, etc. So what I can do with this one is multiply all these through by 2. So I can get K2CR2O7 would be my empirical formula. Okay, so if you end up with a situation where you don't have a whole number, you might have to multiply through by some common factor to clear that decimal off. Okay, this one we don't have to. This one ends up being whole numbers for everything. And again, with real experimental data, you may not get perfect numbers that come out to be perfect. You may get something like 2.01 or 1.99, 1.98. You can round those because real experimental data is seldom going to be perfect. Okay, now we want to answer the second question, which is how can you determine the molecular formula if you know the empirical formula, which we just found, and the molecular mass of the compound is given. So let's take a look at that, and we're going to take a look at that on the next page. Okay, so our compound is C2H6O, which we already found. Now the question is, assume that it was found by mass spectrometry. So remember, mass spectrometry is that fancy instrument that allows us to measure masses of atoms, molecules, isotopes, all kinds of stuff. So determined by mass spectrometry that the molecular mass of this same unknown compound that we found, this C2H6O, is actually 138.2 grams per mole. So remember, this is not the molecular formula. This is the empirical formula, which means that is the simplest formula you can have. And remember again, C6H6, benzene, the empirical formula is CH. So we could have this real compound could be something more complicated than this by some factor. Okay, so what is the molecular mass of this same unknown compound is 138.2. What's the molecular formula of this unknown compound? We have the empirical formula, we don't know what the molecular formula is. So here's how we do that. Let's sum up the masses of these different elements, and we're going to call this the empirical mass. So the empirical mass for this is going to be 12.01 grams per mole. That's the mass of carbon times 2 of them, plus 1.008 grams per mole times 6 of hydrogens, plus 16.00 times 1 hydrogen. And if we do that, we end up with 46.07 grams per mole, or we can round it to 46.1 grams per mole. That's the empirical mass for this empirical formula. Okay, if we add up all the elements in it and find out the mass, that's how much 1 mole of this will weigh. So then our next step is to compare the empirical mass with the molecular mass. So that's step 1, find this. Step 2 is compare empirical mass with the molecular mass. All right, so we notice in this particular case, this one's 46.1, this one's 138.2. Okay, so they're not the same, and that tells us that the empirical formula is not the same thing as the molecular formula. Now, if this was 46.1 or somewhere around 46.1, that would tell us that the empirical formula and the molecular formula are the same thing. A good example of this would be something like H2O. The empirical formula and the molecular formula are going to be the same thing for water because there's no simpler form of it. Benzene and CH are not going to be the same empirical formula and molecular formula. So what we're doing is we're comparing the empirical mass, 46.1, with the molecular mass. We find out that they are not the same. So how do we deal with that? So what we do then is we take the molecular mass and divide it by the empirical mass. And that should give us some whole number, which is the relationship between the molecular mass and the empirical mass. So that's going to be 138.2 grams per mole divided by 46.1 grams per mole. The units are actually going to cancel, and that's going to be approximately equal to 3. So that tells us that the molecular formula is a factor of 3 times greater than the empirical formula. So, therefore, what we can do is we can take the molecular formula, or the empirical formula, C2H60, and we can multiply the whole thing, all the subscripts through, by 3, which will give me a formula of C6H18O3. That must be my molecular formula. Okay, so using this technique, we need to be given a little extra information. We would need to be given the molecular mass of whatever that compound is. And again, mass spectrometry is the way you would figure that out. If you figured out the empirical formula and you're given the molecular mass, then you can figure out what the molecular formula is. Now, the last point you might be wondering at this stage is you might say, well, 46.1 times 3 is not 138.2. It's actually 138.3. Well, we've done some rounding. This was actually 46.06 something. So by the time we do that rounding, that will account for this. But if they're close to each other, that's why I put approximately equal to 3. You should get something very close to a whole number, then that's the whole number that you're going to multiply this through by. Okay, that wraps up this concept.